Good afternoon, everybody, and welcome to another Geo-Institute live stream as part of our Summer of Live 2024. It has been fantastic. We will continue to go for another couple weeks. You can find out more information about all of our live streams up at our Eventbrite page. We would encourage you to watch those as well. My name is Brad Keeler. I'm the director of the Geo-Institute, and we are really happy to have you with us today for Kyle Rollins' third and final live-streamed Cross-USA lecture. If you don't know anything about the Geo-Institute, after you watch this lecture today, head over to geoinstitute.org, and there, as long as you got the time, you'll find out a lot of things about GI, including that we're a technical society. We have about 12,000 members, most of whom are geotechnical engineers and or geologists, and that we are part of the American Society of Civil Engineers. If you like what you see today, and how could you not? Kyle's got his BYU blue on. He's going to deliver a fantastic presentation. Click like, subscribe, and get notifications, and we will let you know every time we post something to the YouTube channel. One more item today. First, before we get to our sponsor message, the Cross USA lecture is now getting to the point where it has a long and storied history. It was started in 2010 by the Geo-Institute as a way to get world-class speakers out to our chapters. So this went on for about 10 years, and in 2020, some stuff happened, maybe you remember, and we had to live stream a couple of the Cross USA lectures at the end of the year from Bob Bacchus that year, and that became a new tradition for us. So every year we live stream a couple of the Cross USA lectures in the summer, and it has become a big hit. A little bit more about the Cross USA. It is a joint effort. The lecturer every year is chosen by the Board of Governors, the Local Involvement Committee, and the Grad Student Leadership Committee. Those groups come together, pick an excellent lecturer, and then chapters bid in to host the lecturer. And the lecturer goes to those chapters, gives the lecture, and makes it honestly out to a bunch of other places during the year too. The amount of lectures that Kyle gave this year is, we'll call it amazing. It's a large number, and he should be very proud that he got out to all of those groups. Our Cross USA lecture for 2024-25 is Richard Bathurst of Royal Military College in Kingston, Ontario. He will be beginning his tour in just a few weeks around this great nation of ours, and you can expect to see some live streamed lectures from him next summer as well. If you would like to make a nomination for the 2025-26 Cross USA lecture, in just a few months we will put out that call. We would encourage everyone to make those nominations, and the deadline for those will likely be right after New Year's 2025. So be on the lookout, and we would love to get your nominations for that year's lecture. So before we get to Kyle and before we get to Mo, who's going to introduce Kyle, we are very fortunate to have a sponsor for the Cross USA Lecture Series this year, and it is GeoPeer, and we have a brief message from them.
What a great intro, Brad. I would like...
Well, first we got to thank GeoPeer. We'll thank GeoPeer for their sponsorship, and then I want to shoot it over to you, Mo. Mohammed El Ahmad is here to introduce Kyle today. He's a new member of our Grad Student Leadership Council. We're very happy to have him. And so now I'll send it over to you, Mo, to introduce our speaker today. Kyle, take it away.
So First, I'm Hamad Al Ahmad. I'm a PhD candidate at Villanova University, specializing in geotechnical earthquake engineering. So that's why I'm really honored to be moderating this USA lecture by the great Dr. Kyle Rollins. So let's talk more about Dr. Kyle Rollins' background. So Dr. Kyle Rollins received his BS degree from Brigham Young University and his PhD in civil engineering from the University of California at Berkeley. After working as a geotechnical consultant, he joined the civil engineer faculty at BYU in 1987, following after his father, who was previously a geotechnical professor. His research has involved geotechnical earthquake engineering, deep foundation behavior, bridge abutments, collapsible soils, and soil improvement techniques. He has published over 190 technical papers and supervised over 130 graduate students. Hopefully, he's going to supervise me soon. He was recognized as the Engineering Educator of the Year by the Utah State Engineers Council and received the Governor's Award for Science and Technology in 2017. ASCE has recognized his work with the Huber Research Award, the Wellington Prize, the Wallace Hayward Baker Award, and the Seed Lecture in 2000 and the Seed Lecture. So also in 2009, he was the Cross-Canada Geotechnical Lecturer for the Canadian Geotechnical Society. And in 2013, he received the Jorj Osterberg Award for Innovation in Foundation Testing from the Deep Foundation Institute, DFI. So you have the floor now, Dr. Kyle Rollins. Thank you so much.
Thank you for that kind introduction. Let's see if we can get this up and working here. Right. Seeing this okay? Wonderful. Okay. It's a pleasure to be with you online, and I appreciate this opportunity to share some of our research with you. And I also want to thank GeoPeer for sponsoring this lecture series. This is the start of a new semester at BYU, where I teach. And this is always a great time because none of the students have had any trouble with the exams yet. And the football team is undefeated. So we don't know how long that will last. But it's a good thing to be undefeated, even if you haven't played anyone yet. Today, we're going to talk about lightweight cellular concrete and its use for MSC and reinforced concrete cantilever walls. And we're going to discuss how large-scale testing that we've been performing can help us understand what's going on with this material. My co-PI on this work is Ryan Ma. He's a principal engineer with Gerhard Kohl in Salt Lake City, Utah. Ryan and his company have done a lot of work designing lightweight cellular concrete retaining structures in the Western United States. This work has been sponsored by a Federal Highway Pooled Funds study. Utah DOT is the lead agency, and we have these other 7 or 8 states that are helping us, and Federal Highway, Jennifer Nix with Federal Highways helped us with some additional funding. So we're grateful for all that support. And just as important has been the in-kind donations. Cellcrete has provided all the cellular concrete, the crew to do the placement, and without them, we could not have had the scope of work that we've done. We also want to thank Reinforced Earth Company and SSL, who provided the rib strip reinforcements and the welded wire reinforcements for all our testing program. Grateful to them. And Gerhard Kohl donated some triaxial and direct simple shear test capability for our study. I'm sure a lot of you are familiar, maybe most, with lightweight cellular concrete. It has different acronyms for it. I'm going to use LCC in my lecture today. It's made of 3 components, water, cement, and a foaming agent that produces all these small air bubbles that you see here. There's no aggregate in the mix. The material that we're going to be talking with, there's different classes, and the material we're going to primarily be dealing with is class 2 concrete that has a maximum cast density of between 25 and 30 on average, with a minimum compressive strength at 28 days of 40 psi. Class 4 might also be useful if you're trying to produce a wearing surface that won't be as susceptible to deformation as class 2. There are a number of benefits for using lightweight cellular concrete, LCC. One, of course, is the lightweight, and this naturally reduces the settlement you have to deal with, particularly where there's critical structures where you're trying to construct. You can also look like a superhero and lift these great big blocks of concrete that only weigh about 20 or 30 pounds, right? Another selling point is it's easily excavated. So if you need to get under that fill material, you can do so with a backhoe without too much trouble. It's recyclable. It just you can roll over it and it goes back down to cement powder, basically. There's a reduced number of trucks that you have to provide because you're not dealing with all the aggregate that has to go in normal concrete. It's easy to place. You can see how they're pumping it into a project here at the Salt Lake Airport. It has good flowability. It's self-leveling. And one thing that's important to consider, it's about half the price of geofoam, which is quite a bit lighter, but can often solve a lot of those same problems that you might be looking to deal with. So there's been a number of LCC projects in Utah. Bangerter Highway used cellular concrete for retaining structure you see here, and the Points project had a concrete vault that needed to be left open, so they had this retaining system behind it with cellular concrete. That's a block masonry wall. And there's been a number of cases where sliver fills were used to add cellular concrete adjacent to existing roadways with conventional backfill. Even though we're using it, there's still a lot of questions about shear strength, for example. One approach might say that, well, it's basically a frictional material, so let's use a friction angle and maybe a little cohesion. So some work by Tawari et al. Suggests maybe a friction angle of 34 degrees with a cohesion between 700 and 1600 PSF. So it looks kind of like a normal Moore Coulomb envelope for soil. Another view is that it's more like a cohesive material, more like a cementitious material. So maybe we could approximate the cohesion as being half of the unconfined compressive strength, like we do in traditional soil mechanics. Or some others would say, let's treat it more like a concrete. Let's use the shear strength of unreinforced concrete, 2 times the unconfined compressive strength to the 1/2 power. So in this case, we'd basically have a constant shear strength with normal stress. Another approach would say maybe it's probably some composite material, and this is suggested for soil mixed walls by Phils and others, Virginia Tech. So you would take the compressive strength Moore circle and the normal and the tensile Moore circle and put a line through those and use those that boundary line in red for your strength. There's also questions about the failure mechanism and pullout. So let's think of this. Does the failure surface look like a bilinear shape, like a conventional steel reinforced MSE wall? Is it more like this for an extensible soil wall with a friction angle of 34 degrees? Or is it like this, 45 degrees, assuming that the friction angle is 0? Good question. And then there's some questions about pullout. If we're pulling on this wall, is it similar? Is the resistance similar to sand? Is it stronger than sand? Maybe it's weaker than sand. So we're kind of operating in the Wild West in some respects here, because people are trying to be more economical with it, maybe taking some risks, others aren't, so we don't know exactly what might be the appropriate thing to do. We did some tests here at BYU involving passive force behind a bridge abutment. We did some lab tests that were 2 feet high and 4 feet wide. Did some field tests with LCC that was 6 feet tall and 11 feet wide. You can see here out in the field at Salt Lake Airport. And people have back calculated friction angle from our passive force test. And we are seeing basically a friction angle to get the best agreement with theory. We need a friction angle of about 34 degrees with a cohesion between 700 and 1,000. And that fits nicely within the range that Tawari suggested. We also did the laboratory test that I was telling you about, and this is a side view of the MSC wall, or the lightweight cellular wall, and you can see it looks kind of like a log spiral shape here. And this is another view. And if you look at that failure geometry and consider it more like a soil, you can back calculate the friction angle, and it would be something like 34 degrees here. Okay. So some of the pieces are coming together, but there's a lot of unknowns and uncertainty. So the objectives of our project were to characterize the nature of the strength criteria based on failure in large-scale tests rather than just very small element tests like an unconfined compressive strength. We wanted to see the failure mechanism that's involved for reinforced concrete cantilever walls, we'll call RCC walls, with unreinforced LCC backfill. We're looking at wall pressures and wall deflections that might develop. We wanted to do the same for MSC walls with reinforced LCC backfill. We're looking at wall pressures, wall deflections, and induced reinforcement forces in the reinforcement elements. And finally, we're trying to measure the pullout resistance of, in our case, it was inextensible steel reinforcements at large scale and under variable applied vertical pressures. So our research approach is always this: one good test is worth 1,000 expert opinions. This is what Wernher von Braun, designer of the Saturn V rocket, said. It's not that we don't value experts. We all want to be experts. That's why we listen to seminars and things like this. It just means that we have to have enough large-scale testing to convince us that things are working the way we thought they were, so that we're not surprised. But we also have to have a healthy skepticism for tests. Not all tests are of equal value. Einstein's reported to have said a theory is something that nobody believes except the person who proposed it. He had a lot of experience with theories, of course. And an experiment or a test is something that everybody believes except the person who performed it. Maybe you've had some tests like this yourself, where you're not quite certain that everything was the way you wanted it to be, whether it was compacted properly or where the strain gauges were working or whatever. So we're going to look at some tests today and see what they can tell us so far. We had a series of 8 different tests, first 2 involving RCC walls. Then we did MSC wall tests with rib strip reinforcements, one next to a soil slope, Test 5, we had an MSC wall with rib strip, but lower strength of the LCC, maybe around 70 psi. Then we also did some tests with welded wire reinforcement to get some kind of a comparison between the welded wire and the rib strips. Then we did some large scale pull-out tests with rib strips and welded wire reinforcements. Lastly, we actually did a lateral pile load test adjacent to an MSC wall with welded wire reinforcements. We're going to primarily talk about these first two tests, but we'll discuss some of the other issues and the performance of the other walls. Oh, I should indicate that we'll talk a lot about the pull-out tests as well. This is our one of our large-scale tests on the RCC wall with unreinforced LCC. Basically, we have a 10-foot tall wall with a 10-foot that's 10 foot wide, and on the other three sides shown in red here, we have a steel reinforced frame, and on the insides of those red walls, we have triple layers of plastic sheeting with oil between them to try and minimize the friction on those faces. So we're kind of trying to produce more or less a 2D failure geometry rather than a 3D compressive strength test. We found out from the first test that it's a much more demanding environment if we only apply pressure on one side. So we first applied surcharge pressure, in this case up to 60 psi, near the RCC wall face. And then we used the jacks on the other six foot side after we'd removed the wall on that back side. So here we're trying to see what the difference might be if we're failing without any wall at all. Okay. Each one of those jacks pushes on a 2-foot wide concrete beam that's fairly stiff so that we can keep a uniform pressure but allow the soil, the LCC in this case, to fail where it might want to fail. So this is a view of the wall in our structures lab. It has a load capacity of 1.25 million pounds. On the right, you can see each one of those 2-foot wide concrete distribution beams with the hydraulic jack on top of it. So this is quite an undertaking to get this to work. We had to be careful about it because we knew we were actually going to put these loads onto the fill. We also had digital image correlation cameras that allow us to see the uniformity of the displacement field on the wall face, along with string potentiometers that told us the displacements at the center of the wall. So in our first test, we first built a reinforced concrete cantilever wall, like as shown here. It has a stem that's 12 inches wide and a slab that's 12 inches thick. The wall is designed to fail at the base, and it's basically restrained against sliding. So we're not looking at that sliding mechanism. We're primarily looking at failure of the stem. And there's a long heel to prevent uplift and rotation. So we're expecting failure at fairly small surcharge pressures, maybe 43 psi to deal with the concrete compressive strength, maybe 60 psi to deal with the wall itself. So here's a view looking into the box. You can see the slab and the stem wall. We have pressure plates to measure the pressure that's applied to the wall. And we've got some in-situ pressure sensors and strain sensors. And you can see the plastic sheeting that's meant to reduce friction on the sides. The mixing was done again by Cellcrete. Here's one of their rigs. We would mix it a batch, 1 yard batch at a time. That would be pumped into our box. The students would take concrete specimens that we could then use for the testing. This had a strength of about 100 psi at that test time. The cellular concrete was placed in lifts that were typically 2.5 feet thick, and then we would wait 24 hours and place the next lift to give the first lift a chance to strengthen. And so it was 4 days basically to put this in. So one thing you find out about LCC is there's quite a bit of variability. This chart here is showing unconfined compressive strength versus dry unit weight. This is from Cellcrete from their test results, and you can see that there's quite a bit of scatter about the mean. And our data points are shown in the green and the yellow. And at 7 days, we're on the bottom end, and at 28 days, we're on from the mean to higher end of the range. But you wonder, and we did, how that variability that you see in all the small cylinders that you test might express itself in the large-scale testing that we're going to perform. We wanted to see how well our beams were distributing the load. So here we're plotting the surcharge pressure versus axial strain for this first beam, 2 feet wide, the second beam, and the third beam. And as you look at this, it looks like there's fairly good agreement between the pressure strain relationship being produced by this loading system. This slide shows the surcharge pressure versus axial settlement. And you can see that when we're loading, doing the test with no wall that's shown in blue, we get up to about 44, something like 44 psi of surcharge pressure. And then we start to get a lot of strain taking place. And we can't hold that pressure. The pressure drops off. You can see on the photo on the right that there's this offset in the concrete distribution blocks as that LCC starts to settle. In contrast, if we look at the surcharge versus strain or versus axial settlement for the RCC wall, you can see that the pressure settlement relationship is very similar to the case with no wall, but then we get an additional maybe 20 psi of resistance before things start to settle a lot. And then we get settlements of maybe 2 to 3%. If we talk about this in terms of strain, we're seeing a lot of our displacement take place at a strain level of about 1% for the reinforced wall, and maybe 0.7% for the case with no wall in place. And there's quite a bit of difference that you can see between the behavior of the reinforced with the reinforced concrete wall in place and without it. With the wall in place, we have a fairly ductile load versus settlement, load versus strain curves. Whereas with no wall, we're getting a rapid decrease as we get to kind of a catastrophic failure where the wall just slides into the surrounding air, right? This is showing the surcharge pressure versus lateral displacement. And again, the two curves are very similar until we get up to 44 psi, and then they start to diverge. We start to get a lot of lateral displacement post-peak, and we have a reduction in the surcharge pressure that we can maintain. In contrast with the RC wall in place, again, we get an additional 20 psi before we start experiencing significant lateral displacement. And this added capacity is coming from the moment that was provided by the stem wall and the reinforcing steel that helps produce that. And since we're dealing with the steel, it's a much more ductile failure situation. This plot shows the wall displacement versus height that's measured by the string potentiometers on that concrete wall face. And you might notice that we can get clear up to maybe 52 psi of surcharge pressure before we get more than a quarter inch of lateral displacement. So the wall is really helping reduce the displacements that take place here. And then as we go from 50 to 60, we start to get a lot more deformation, and it's rotating about the base as we would expect. And we can look at the displacement that we had calculate from the DIC system, and it's fairly similar. The DIC also told us that we're the wall is failing pretty uniformly from side to side, which is what we wanted to see. When we take the sidewalls off of the box, you can see the stresses and not the stresses, but the cracking patterns that are developed. So on the free face side, where we took the wall off, we're getting a fairly steep failure plane. And even though we loaded the top of the LCC back to 6 feet, we're getting failure at about 2 feet in from the face of the wall. For the RCC side on the right, the failure is starting 6 feet back from the wall face, and that was the loaded area. And if you put in we put in a vertical dashed line down to mid-height, and then another line going down to the base of the top of the slab. Most of the cracking, the tensile cracking that's taking place is contained within that boundary. So it looks like we've got a bilinear kind of a failure situation. This is a 3D view of the failures obtained from optical means. So on the left side, you can see the free face falling into onto the side. Blocks of concrete are coming out. And then with the RC cantilever wall, that wall is holding things in place and keeping that, allowing that to fail more or less as a block there. If we look at the active failure geometry, if there were no wall, where there was no wall, Rankine failure would suggest a linear failure surface inclined at something like 62 degrees if we have a 34-degree friction angle. And we're seeing a variation on that. It looks something like this. So we think the actual failure mechanism is more like a log spiral than a Rankine failure, but it is more like a true active geometry. Examination of the behavior of this free face wall test gives us a really good opportunity to see how the different failure theories pan out in relation to what actually happened for the free face condition. So one approach would be to use the phi-c, and using a friction angle of 34 degrees is what we used. If we could get a K sub A value, there would be 0.28. And we can calculate the contribution to active force as being the first term, which is self-weight, which is fairly low because of the low unit weight of the LCC. Then the surcharge, which is causing a positive pressure on the wall, positive force, and it's resisted by the third term, which is primarily the cohesion. So this is basically Rankin's equation for a C-Phi material. So we would, failure would be expected for this case at a surcharge pressure of about 42 psi with a cohesion of 1600 psf. So that fits in very nicely with Tawari's suggestion of using these values. And it's consistent with within the range of error of what actually happened. Sometimes people assume that there isn't any cohesion and use just the friction angle. So if we use that approach there, we basically get rid of that third term, which is really the main resistance. So that would be bringing the cohesion down to 0, but still using the same friction angle. So if we were to do this, failure would be predicted. We'd have, when we get the surcharge pressure much above 1 psi. This is certainly far below the measured failure pressure. So it's really impossible to explain stability with these assumptions of 0 cohesion, even though we might use it in design to be conservative. Even if you bumped it up to 40 degrees, you wouldn't be able to explain what happened in the field test here. Another approach is to use 0 cohesion with a 0 friction angle with a cohesion of 50% of the unconfined compressive strength. So in our case, that would be a value of maybe 50 psi. So if we do that, we would predict that failure would have occurred when we had a surcharge pressure of 189 psi. This is almost 5 times higher than the actual failure load that we applied. So this approach doesn't seem to be appropriate. It's going to overestimate our resistance in comparison to what happened in the test in the larger scale. To make this work, we'd need to have a value that's something like 0.2 times the unconfined compressive strength to get equilibrium in this case. And that actually works out to be close to the value that you would estimate based on concrete, unreinforced concrete. So that approach might work. This plot shows the pressure on the cantilever wall. We're plotting it as the surcharge pressure is increased. So 5.5 psi, 17, 23, so forth. And when we start getting close to the failure value, our pressures are about what we'd expect if we had a concrete strength between 30 with a LCC with a strength between try that again. Friction angle of 34 degrees and a cohesion between 1,000 and 1,500 psf. It decreases on the top and the bottom to a lower values, but that's kind of in line with the theoretical pressures we might expect to see on the wall. And the theoretical pressures are computed again with the Rankine equation for C-Phi materials, using a friction angle of 34 degrees where K sub A turns out to be 0.28. We can take all the pressure cells. They have some offsets to begin with, but if we just plot kind of the best fit of the lines of horizontal pressure relative to surcharge pressure, we can get a first estimate of K sub A. And for those different depths, you can see the variation. The average is 0.29, so it's not far off of what we were seeing. We've back calculated the friction angle for each of those, and on average, it would be around 33 degrees. So that's not too far out of line with the 34 degrees we've been looking at. So we noted earlier that that increased capacity is coming from the failure of the rebar, the moment capacity of the rebar. So we said, let's take a stab at that and see if we can deal with it. The pressure that's on the wall is primarily due to the surcharge, and that pressure would be Q times Ka. So if we took and computed the moment produced by that pressure distribution, we'd have 1/2 H is the moment arm, and the force being Q Ka times H. So that would be 1/2 Q Ka H squared. So we can rearrange the equation and solve for the increased pressure Q that we could apply adjacent to the wall to account for the capacity of the RCC wall. So for our wall, we had about 34-foot kips, and the wall was 9 feet tall. So we come up roughly with 20 psi. And if that's the additional resistance that we did measure in the field, roughly that. So we're in the ballpark with this. Now, that means we could use this equation to calculate the increased capacity of surcharge pressure due to the moment capacity of the stem wall using, basic mechanics. And our equation for the total resistance would be this resistance due to the stem wall plus the LCC strength, which would be 2 times the cohesion over the square root of K sub A minus gamma H. Okay, so you could use that equation if you could estimate the moment capacity, nominal moment of the RCC wall and get a first approximation of the surcharge pressure. Okay, let's move on. This is the second, the first test that involved the MSC wall reinforcements. So once again, we've got a 10-foot tall wall. The wall is composed of 2 5-foot tall by 10-foot wide MSC wall panels. And then there's reinforcements that are distributed across the wall horizontally, and they're spaced at 2.5 feet on centers across the 10-foot width. And then vertically, we're placing these reinforcements at 2.5 feet on centers with 1.25 feet top and bottom. Okay, again, we're filling this up with LCC. We're putting plastic sheeting against the side walls to minimize friction on the interfaces. So we first did the test with 6-foot surcharge up to 60 psi or so adjacent to the MSC wall. Then we eliminated the wall and just loaded the hydraulic jacks on the side near the free face wall. And to get an idea what kind of resistance we'd have with very low reinforcement. We prepared strain gauges that were on several of the reinforcements. We put pressure sensors on the wall panels to measure pressure there. We tried several different systems. A lot of them had trouble with water getting into the wiring and causing damage to us. But these plates that were poured flush with the wall survived. I know there's all kinds of uncertainty about that, but at least gives us something to look at. This is instrumented MSC wall panels with plastic sheeting on the side, ready for the first lift. Those are the instrumented rib strips, pressure cells. And the first this is the first lift going into the reinforcements covering the LCC. So the the reinforcements are located at the center of each lift. So there's about 2.5 feet of LCC. So that would be poured. We'd wait a day for that to cure. Then we'd come back, place the next level of reinforcing strips, and then pour that in place. And eventually, after 4 days, we get to the surface that was screeded off. This plot shows the axial strain versus surcharge pressure. Once again, the load versus the pressure versus strain curves are very similar for the case with no wall and the MSE wall until we get up to about 40-something PSI surcharge pressure. At that point, when we're loading against the free face, the resistance drops off substantially, maybe 1/2 of what it was at the peak, and we start to develop a lot of axial strain. In contrast with the MSE wall in place with the reinforcements, we can put on an additional 28 PSI surface pressure until the wall starts to deform excessively. As you can see, the offset between the two is about 3 inches. Again, we're getting a lot of strain or the failure taking place with the MSE reinforcements when this strain reaches about 1% in the average strain in the LCC, and maybe about half of that with the case with no wall. Let's look now at the surcharge pressure versus lateral displacement. This is sometimes a more critical issue, but both axial and lateral are important. Once again, fairly similar behavior. We start to deform a little more. There's a break in the curve at about 20 PSI. At 43 PSI, we post peak, we get a drop off in strength, and the displacement goes up to over 1.5 inches. We stopped the test at this point for safety reasons because the whole wall would have collapsed catastrophically into the structures lab, and we didn't want to damage our sensors and risk hurting anybody. Then the other case with the MSE wall, we can apply again another 20-something PSI surcharge pressure before we get failure. So this is a photo of the failure of the free face wall. You can see it's ready to go. These blocks are coming off in chunks. The additional capacity that we're getting from the strips is on the order of 20-something PSI. Again, contrasting the behavior, we have a brittle behavior with no reinforcements and a fairly ductile behavior with reinforcements in place. This plot shows the wall pressure from the base of the wall, and this is showing lower wall pressures than we saw with the RCC wall. And I think we'd expect that to be the case because the reinforcements are picking up some load that doesn't get transferred to the wall face. If we compare the RCC wall pressures, we're dropping maybe, I don't know, roughly half, except for that one level at 4 feet. So things look like they're behaving like we'd expect. Again, the theoretical values are computed using Rankine theory for CFE materials. What about wall displacement? This plot shows the displacement of the wall from the base to the top. Once again, we have to get up to a surcharge pressure of 55 PSI, fairly high, before we start to see more than 1/4 inch of displacement maximum on the MSE wall face itself, lateral. As it starts to get to the failure state where we have excessive deformation, you can see that we have a maximum displacement at the joint between the two wall panels. It still doesn't look that terrible, but there is a displacement of 1.7 inches at that joint. But we had to get to a case where we're almost ready to fail before we started to get a lot of excessive deformation. At this point, the reinforcements have failed in Pullout, as you'll see later. Again, here's the free face side on the left and the MSE wall face on the right. The failure surface is very steep at the free face. It starts initiating about 2 feet back, even though we loaded the 6-foot side. And then on the MSE wall side, again, you can maybe see that there's a kind of a bilinear shape to the failure where the cracking is severe, the tensile cracking is developing. So it's more like what you might see for an MSE wall in soil. This is a comparison of the surcharge pressure versus lateral displacement curves for the two cases where there's no wall. And even though the strength is a little bit different, two different tests, the surcharge pressure versus lateral displacement curves with no wall in place are very similar. Likewise, with the MSE and the RCC tests, the surcharge pressure and lateral displacements are very close to one another. The RCC developed its resistance a little more gradually to get that additional resistance, whereas the MSE reinforcements pick up resistance faster and then have a little bit of a drop off. But in both cases, with either the RCC or the MSE wall, the failure or the displacement doesn't represent a big drop off in resistance. I'm going to jump ahead and show you resistance for all the axial displacement versus surcharge pressure for all the tests with the reinforcements. On the left is axial displacement versus surcharge, and on the right is lateral displacement versus surcharge. You see more variation in the lateral displacements, but overall the behavior, especially axially, is very consistent. And this to me is quite surprising, considering the fact that, as I pointed out earlier, there's a lot of variation in the strengths that we get from the various tests. And even with the sliver fill, we still get a lot of resistance, similar resistance with a wall that has lower strengths. We're still getting a good behavior. So we're going to look now at pull-out resistance testing. We had this system in place so that we could do pull-out tests in one of the situations where we had different reinforcements in place. And we loaded the entire area uniformly and then pulled the reinforcements out through holes in the reinforcement in the retaining wall or the wall panels. So we had some with rib strips and some with welded wire. Again, we pulled them out through these holes. We found out we needed to do some supplemental tests, so we did some additional testing with blocks that were about 3 feet tall, and we put dead weights on top to get some additional information. There was 8 additional tests with these smaller blocks at a little larger pressure. And here you see the pull-out test taking place. this shows some of the geometry of the welded wire reinforcements that we tested. These are load deflection curves for the rib strips. You can see that they tend to reach a peak at fairly small displacements, in some cases a tenth of an inch or maybe a quarter of an inch, and then there's a tendency for this to drop off. When that would happen, there was a big popping sound. We suspect maybe this is where we're losing some of our cohesion, and maybe the friction is taking over. We picked our resistance as the maximum value within 0.75 inch of displacement, right? So we would have picked this value here. We'd have picked this value here for the rib strips. In contrast, with the welded wire reinforcements, as we're loading them up, we get even more resistance as we displace the reinforcement. And at our value that we're picking off as our maximum here, within the maximum within 0.75 inches, we haven't developed the full resistance for the welded wire. And for this maximum, we might have an additional 30% resistance if you wanted to allow that kind of displacement to take place. We're trying to limit the displacement, so we use this value. We exhumed the reinforcements, and you can see that here as we pull on this longitudinal bar, the crossbars develop passive resistance on their face, even though we're treating it as frictional thing, and a gap forms. So as we're pulling this way, you can see the gap that forms in the LCC behind that crossbar. After exhuming it, you can clearly see that bar is pulling to the right, and we basically pulverized this material behind it. For the reinforcements, they start out looking like this. As we pull out the rib strip reinforcements, and a number of our cases, it looks like there's still some LCC adhering to the reinforcement as it's being pulled out. As you can see again here. We back calculated our apparent friction coefficient, F star, for pullout using the maximum pullout resistance within a quarter of an inch, or within 0.75 inches. We divide it by 2 times the width and the length and the vertical stress that we have the reinforcement under. And we're assuming that all the pullout resistance from this equation is frictional, but it's really an apparent friction because some of it's coming from passive resistance as well. So this shows the blue dots are the F star values that we had. Here's a tentative design recommendation with linear segments. And these are the BYU tests in blue. These are the tests from SSL company that they did in connection with a Caltrans project. And you're seeing that there's a tendency for the F star to decrease with increased confining pressure. Near the surface, down to 1,000 PSF pressure, we're getting higher F star normalized by the spacing here compared to what we'd get for soil if you take 20 feet and multiply it by the unit weight of the Cell-Creek concrete. Okay. We did something similar with the welded wire reinforcements. These are the welded wire reinforcements. I think I've got a slide out of place here, but these are the welded wire reinforcements. I think the first one should have been for rib strip reinforcements. Now we thought, are we down here for high enough pressure? And we thought, well, sure, we're high enough for like 50-foot wall maybe here. But if you think of the condition we're loading in our lab tests, our pressure is going to be a lot higher than that. It might be up to 1,000 PSF, and our tests just don't extend to that level. So we went back and realized also that if someone builds a bridge abutment out of LCC like they're doing in Washington State, the WashDOT people are doing, which is 65 foot high, and it's going to be supported on a slab footing here, you could have some fairly substantial values of pressure. So we went back in and put some additional blocks. Here's our reaction beam with tie-down anchors. This is the hydraulic jack. It's applying pressure to the distribution beam to distribute the pressure across here. And this is our LCC test block that we're pulling the reinforcement out. So we did some additional testing at higher pressures from 30 to 60 psi. Now, when we look at F-star values, we tend to go at the very low end of the range. This is some results plotted by Reinforced Earth Company. This shows a comparison of AASHTO values with some tests at Texas Tech, I believe. And there's always a large variation in the pullout resistance factor that's back calculated, but it decreases with depth or pressure. But typically, we're going to use a value near the lower end of the range. And so that's what we decided to do here, is come up with a value that would go through all the range. And these last three are those higher pressures that we developed. Okay. And rather than doing different straight line segments, we've used just an equation that is applicable all the way through it. It's kind of at the low end of the range of materials we've tested. And here's the welded wire, another equation for it that's doing a fairly good job of bounding the low end of the results. Last thing we want to look at is MSE wall stability without reinforcements. And we wanted to do this with using slope stability methods, and then use the same properties that we back calculate there in analyzing the behavior with the reinforcements. So we used Stephen Wright's program, UTexas 4, which he, of course, recommended in his lecture. I think it was a seed lecture several years ago, because it has the ability to handle this properly. We used a LCC shear strength defined by a friction angle of 34 degrees, and we used the cohesion of 1600 PSF that we'd found from force equilibrium. We used a unit weight of the LCC of 30 pounds per cubic foot and applied this variable pressure on the surface of the model. Then we started increasing pressure, and to get failure, we have to increase the pressure to about 44 psi, which is what we measured in the field. And these are the critical failure surfaces for that case, and agrees reasonably well with what we saw in the test. So that gave us some confidence that this might be a valid approach. We had 4 different tests where we had a failure of the free face. And for each of those, we used a friction angle of 34 degrees. There's some differences in unit weights, differences in unconfined compressive strengths. And we back calculated the cohesion that would it take to have a factor of safety of 1.0. So this is the range, a lot of them in the 600, 1600 PSF range. This one test where we had some lower strength concrete was in the 1200 range. So somewhere between 1200 and 1700 PSF was our back calculated cohesions. Then we went to analyze the wall stability with reinforcements, I should say, with reinforcement. So we use the same test or same slope stability model with Spencer's method, satisfies both force and moment equilibrium, is designed to deal with reinforcements. We used the back calculated values from the free face tests with the appropriate unit weights, and then the pressure on the wall that was involved. And in back calculating this from the reinforcement, we got an equivalent force for a 1 foot wide strip. We distributed the reinforcement that we had linearly across the strip. And then we kept all the LCC properties the same as back calculated from the free face test. So all we did was adjust the F-star value until we got a factor of safety of 1. Of course, as this fails, for any failure surface, we're only taking the tensile force at the back end of the reinforcement. So if we do that, I'll show that slide again that showed the pullout resistance in our boundary curve. Here are the back calculated F-star values using the slope stability model. And the back calculated values are in very good agreement with what we got from the pullout tests here. It's 3 tests that we're looking at there. And then this case involves welded wire reinforcement. So I'll put the curves up for the welded wire. And this point comes in very nicely with the results from the pullout tests that we've done previously. So that was very satisfying after finding out that we couldn't get it to fail if we were using values like we were seeing up here at lower confining pressures. So let's summarize here and note that both the MSC and the RCC walls with LCC backfill can withstand significant surcharge pressures with limited axial and lateral deformations in the order of 50 psi. Failure occurred at surcharge pressures of 62 to 67 when the UCS, unconfined compressive strength, was around 100 to 120 psi. The MSC and RCC walls significantly increased the failure load in comparison with LCC with no wall in place and produce much more ductile load deflection curves. If we look at the free face failure situation, the LCC strength was best predicted using a C-phi model rather than taking half of the unconfined compressive strength. There's a possibility that we might be able to use like the of the shear strength of concrete for unreinforced conditions. But this using UCS over 2 didn't work very well. The earth pressure with the RCC was consistent with what we'd expect if we used Rankine theory with a cohesion of 1,000 to 1,500 PSF, for example. The horizontal pressures on the MSC wall were about half as large as those for the RCC wall because the reinforcements are picking up load. Wall deflections for both the MSC and the RCC wall were less than about ½ an inch until we were getting very close to failure. The moment capacity of the stem wall is increasing the resistance to surcharge and can be accounted for by using the moment capacity of the stem. The MSC reinforcements themselves provide the additional shear resistance to surcharge, and you can account for their effect using slope stability techniques. Lastly, some preliminary observations and conclusions for design. The moment capacity of the stem wall increases the LCC resistance to surcharge load, and we can use the moment capacity from the ACI code to account for that increased resistance. The MSE reinforcement design in the LCC can be determined using slope stability methods. Of course, you could do the regular pullout testing, but to see if the lengths and spacing are acceptable, you could use a slope stability model using the F-star versus pressure curves that have been developed in this study. Along with slope stability methods such as those in UTexas too. Having the steel reinforcement in the RCC stem and the MSE walls themselves result in a much more ductile failure mechanism in contrast to the brittle failure that occurred with unreinforced walls at a free face. So we think it's worth the money to put the reinforcements in place to lead to a ductile behavior rather than some catastrophic failure in unreinforced material. This the results of this study are being put together, and it's in a final report that we're supposed to have done in the next couple months, and that'll be available on the UDOT research website that you can access. We're also working on a couple of papers that will summarize the results of these tests. And with that, I'll end. Thanks for being online and listening to this presentation. I appreciate it very much.
Thank you so much, Dr. Guard, for this great lecture. It's really fascinating to see the depth of the large-scale lab work you've shared with us. Can you hear me, Dr. Guard?
Yes.
Yeah. So I'd like to remind everyone, if you have any questions, feel free to drop them in the chat box below and we will address them shortly. I have one question of my own. In test 2 large-scale test on the RCC wall with unreinforced LCC, I was wondering if that black base is acting as like a rubber pad to reduce the load effect on the beam directly. You also mentioned something about like using oil.
Oh, yeah. So on the side walls, we put in 3 sheets of plastic with silicone oil in between each of them. And the idea there was that we would reduce the friction on the side. So we're constraining it to fail more like a 2D geometry, as if the wall wasn't there. Of course, there is some friction that's taking place there.
Yeah, I thought it was like protecting the beam from being like punched or something.
No, the beam was just sitting there, but we blocked it in so that it couldn't slide.
Okay. So we have another question from Cellular Corporation of America. So one of the question is, were the full-scale test conducted at 28 days to allow the LCC to fully cure?
That's a really good question, and the answer is no. If we had waited the full 28 days, we would have had a strength that was on the order of 200 psi, and we think that's maybe a little unusual, and so we wanted to have a strength that was a little closer to what people might see in design. So we accelerated the testing and did it earlier, so that our strengths would be a little more consistent. We're already at 100, which is the minimum requirement is 40 psi, and we're at 100, 120. The other problem was that if we had gone a whole lot higher, we wouldn't have been able to get to failure with our load frame. It was already a fairly massive frame, and so for those reasons, we did that.
We have another question from Jim Heckby. What is the current thinking about the long-term strength reduction breakdown of LCC?
Yeah, really good question, Jim. This is the million-dollar question, I suppose. There have been a number of structures that have been in place for a number of years. BART has some structures like this and others, and they seem to have been able to remain intact. Now, that's not an environment that has a lot of shrinkage and swelling and freezing and thawing like we would have in Utah. But overall, I think performance has been pretty good, but there is still a significant concern about long-term durability and degradation. So when we showed some of our results to Reinforced Earth Company engineers, their thinking was that for the time being, we probably shouldn't use the full cohesion in calculating the pressure on the wall. Because if we did that, we would probably have cases where the design would say we don't really need reinforcements, even though it's a good idea in our view to put them in place. And it's possible over time that there could be some degradation of the LCC, which would make it have a lower strength or degrade its cohesion. So our recommendation at the present time would be when you're calculating pressure that you neglect the cohesion and just calculate the pressure due to the surcharge and the self-weight of the concrete, but then use the value for F star that we've gotten here in calculating the pullout resistance.
Okay.
Go ahead.
Thank you. So we have a third question from Pete Slocum. This one is interesting. So would we expect the cold joints affect the strength? Often LCC is installed on the West Coast continually slowly and not with a series of cold joints vertically.
Oh, well, that's a good question. In our case, we put the reinforcements at the center of the lift. So when we're calculating our pullout resistance, it's in the middle of the lift. We do have a cold joint at 4 locations, but when we exhumed things, we could see where that boundary was clearly. We didn't see any offset that was taking place or any excessive deformation or yielding at that point. So we don't think that reduced the overall capacity of the system. Now, one of our TAC members from Oregon suggested that we do some tests where we have a cold joint and we test at the interface. And we did find from some large scale direct shear tests that were about 18 inches square, that we had a reduction of about 40% in the interface shear strength at the cold joints. Okay, so it is a real thing, but it's we didn't observe a problem with it in these surcharge tests that we did.
Okay, so we have another question from John Macmillan. So the question is, irrespective of wall face details, would the inclusion of reinforcement like GeoGrid in the LCC fill aid in producing a more ductile fill failure should such occur?
Yeah, of course, we haven't done any testing with extensible reinforcements, but they have been used. Like I think they've been used on some fills in California for the BART system and others. So one of the advantages of the steel reinforcement is that we pick up that resistance quite quickly with very little deformation. I think that the GeoGrid kind of structures could still be successful, but the behavior might be different than what we're showing in these tests. There may be a little more deformation that needs to take place to fully develop the resistance of the reinforcements. But I think it could probably be small enough that it could still be used. Maybe you don't get quite the same amount of extra capacity, but it might be a situation where you may not necessarily need it to begin with. So, you know, we're always looking for something else to do. So we'd be happy to do some tests like that. We kind of followed the guidelines and the desires of our sponsors in doing the work, and it was all metallic reinforcements.
Another question by Shisela Kenny. Did you consider the effects if the reinforcement is located at the cold joint between LCC lifts?
Could you give me that again? Something about the cold joint?
Yeah, did you consider the effects if the reinforcement is located at the cold joints between LCC lifts?
No, we didn't have any information on that, but I'm suspecting that it would be reduced. It seems like a better approach to eliminate that concern and put them put them so that they are inside a lift. That was the approach we took here. I think there would be some reduction by having them at the cold joint, but I don't think it's going to. I don't know how to answer that question without some test result to guide me. But I'm certain there'll be some reduction.
We have another question from James. Does LCC lose strength when subjected to cyclic loading?
There's going to be some reduction in resistance due to cyclic loading, yes. All our tests were monatomic, so we're progressively increasing the load. We did have some tests where we dropped, I shouldn't say all of them, but where we did drop off the load and then reload again. And we didn't see any big drop off in resistance from that. Just a few cycles, but this is something that could conceivably, if you're cycling it in two directions, then when you're coming back on the next load and you'll be loading inside that gap, I can imagine that you'd have some reduction in resistance. But none of our tests involved cases where we're loading in both directions. I know there's been some tests that have been done at UC San Diego where they had reinforced walls, and they seem to perform fairly well under cyclic loading. I'm thinking of the wrong place at Jorj University in California.
Another question by Fathi Al-Sayed. So how would the results change with the use of type 1L cement in LCC?
Yeah, ours are all type 2 concrete, and our experience, although limited with the type 1 and the limestone, is that you get more erratic performance and more variability in what you're seeing. I can see the rationale for using it, but in terms of understanding and being able to predict better what's going to happen, I like the older design. And my colleagues suggest that work this more routinely, suggest you may need to up the cement content to get things to give you a little more certainty of what you're going to get.
So we have another question from James. So is there a required pavement section thickness or pavement structure number when placing a pavement section directly on LCC?
There is a requirement if you wouldn't want to put the pavement directly on this class 2 material. So similar to what you have with geofoam, you have to have a wearing surface that's a higher strength material. And different people will use different things. Some can use lightweight cellular concrete, but I think in many cases, a regular concrete might be involved. So that's a little beyond my background on this at the moment.
Okay, so another question by Nathan Hackney. Will there be a published study based on the work you have done in the near future?
Yes, like I indicated, several of the reports are already published online. But the overall final summary we're working on right now, about halfway done. And I'm hoping to get that done in the next 2 months so we can have that available to everybody. We're also working with Ryan Ma to produce a paper on the pullout resistance and the other analyses we've done.
Okay, so this is all the questions. Thank you again for this insightful presentation, Dr. Kyle, and I'll now hand it back to Mr. Brad Keller to wrap things up.
Fantastic. That was amazing interaction from the audience again. Kyle, you turned in 3 gems this summer. We really appreciate it. Mo, great job moderating today. Fantastic. It was a little bit of a trial by fire with all these questions for your first time, but you did a good job. For all of our viewers, if you liked what you saw, and like I always say, you're here at the end, so you probably did, remember to click like and subscribe and get notifications, and we will let you know every time we post something to the YouTube channel. This is, as we said at the beginning, Kyle's final live streamed Cross USA lecture. We're coming up to the end of his year as Cross USA lecturer. I wish that you could hear everyone out there. I would tell them to give you a big round of applause for all the amazing lectures this year, getting out to all these different places. We do really appreciate it. And I have to say, you're one of the most humble people I have ever met in my life. We appreciate that so much, and it really comes through when you present, and it's so genuine. We loved having you this year as the lecturer. It was a great experience, and I hope it was a lot of fun for you.
It was. Thank you very much. I'm delighted to have been able to do this. It's fun to meet all the people around the country and see all the good things they're doing. It's really exciting.
And so, like I said, that wraps up our Summer Cross USA lecture series. If you watched all 3, fantastic, great job. If you didn't, you can go back and watch them on the YouTube channel anytime you wish. Go check those out, as well as our SCADs, that's the technical term, of other videos that we have up on the site. Director's Cut, Geostrata Extra, you name it, they're all there. In fact, we have 4 new episodes of Director's Cut this week, the way we do every year in the week after Labor Day. You will want to go check those out. Yeah. Our next live stream, we actually have 2. Next Thursday, a week from today, the first one in the morning will be the premiere of the Geo Legends episode featuring Paul Main. He was interviewed by Dean Harris, so you're going to want to watch that one. And then in the afternoon will be the first sneak peek for our Geostructures conference that we're running in November. Sebastian Lobo Guerrero of the American Geotechnical and Environmental Services, Inc. will be presenting on the I-579 CAP project in Pittsburgh. You don't want to miss that one either. The link is in the chat to our Eventbrite page where you can register for all our upcoming live streams. Thanks again to GeoPeer for their generous sponsorship of the Cross USA series. It will continue with Richard as our lecturer next year, so be on the lookout for a lecture in a town near you, and then next summer the live streams as well. Matt Roberts was our producer today. Thanks again, everybody, for watching, and we will see you all very soon.